Namaskar and welcome back to the course on statistical mechanics of phases and phase transitions. We are studying quantum systems, and in particular, we are studying the transverse field rising model, which is a model made out of qubits placed on a chain and has a global Z2 or rising symmetry. It has two energy scales, an exchange coupling scales, which wants to align this qubit degrees of freedom parallel to the qubit z-axis on neighboring sites, and we have a transverse field H which wants to place them along the qubit x direction. Our goal is to obtain the ground state phase diagram, and we performed perturbative calculations, and the outcome of the perturbative calculations was that when the transverse field is much smaller than the exchange coupling, then we have a broken symmetry state with an order parameter that is non-negative. In the opposite regime, where the exchange coupling is much smaller than the transverse field, the system retains its Z2 symmetry, and the question we were asking is, as you change this parameter h by j, how does it go from this ferromagnet all the way to this symmetry preserving state that is obtained when j is equal to 0. So, based on our perturbative calculations, we were able to rule out the possibility of crossover, because we found that even for a small value of j, however small, namely a very large value of h by j, which is not infinity, which is a finite number, we found that the magnetization is 0, and therefore the system is in a Z2 symmetric state. What we have not resolved yet is whether which of these possibilities is the correct answer. Is it going to be a first order transition, or is it going to be a continuous transition? This is something we have not resolved. Now, we know that the system has a finite excitation gap at this end of the parameter space as well as at this end of the parameter space, and we were able to interpret the excited states as if there are some particles moving in the system. The excitation gap can be thought of as some mass energy required to create the particles plus the energy that they gain by dispersion, namely they have some kinetic energy which they gain by hopping around. And this was an interesting result from the perspective of broadly making toy models which explain some phenomena that we see in nature. But we were left with a puzzle at the end of the last lecture, which is that the results for the two sides, namely h much less than j and j much less than h, could be obtained from each other by simply interchanging h and j. So, while that looked very interesting, it also was quite puzzling, because it was not quite clear why something like this would happen or whether it is just some accident. So, what we will do in this lecture is we will try to resolve the puzzle as to why you are able to exchange h and j and get the results on either end of the parameter space, and we will try to provide some arguments to answer this question, which is, which one of the possibilities is the correct one? Is it the continuous phase transition or it's the first order phase transition? So, you have to stick around till the end of the lecture to find the answer. Okay. So, the puzzle came to us via a table, and the results we summarized at the end of last lecture was that the ground state energy looks like this when h is much smaller than j, and if j is much smaller than h, it is exactly this expression with h and j interchanged. Except for magnetization, anything associated with energies, you see h and j get interchanged. So, how do we understand this, and how do we make sense of something like this? And in fact, we can go a step further. If we make sense out of this, can we use the insights we gain to say something interesting that we cannot otherwise. So to do this, we have to go back to the drawing board, so to speak. We have to go back to the transverse field Ising model and look at it, the way we constructed it and the operators, etc., more carefully. So we'll go back to the transverse field Ising model. So let me just revise very quickly what we have done, how we constructed the model. We placed qubits on a chain. So each of these sites have a qubit, and the qubit Hilbert space is two-dimensional. It is spanned by two orthonormal states, and those orthonormal states we constructed as the eigenstates of the local meaning belonging to the qubit Zi operator, and the eigenvalues can be plus or minus 1. The Hilbert space of the full model, so this is the many body or many degree of freedom Hilbert space, is the tensor product of this full Hilbert space. And the dimension of this full Hilbert space is 2 to the power n, because I can construct tensor product basis states out of the local Z polarized states of each qubit, which can take plus or minus 1. And when I tensor product all these combinations, I can get 2 power n distinct states. We put down a Hamiltonian, and the Hamiltonian was, or is I should say, written down in the following way. There is this term which promotes spins on neighboring sites to be Z polarized in parallel, and there is a term which wants to simply polarize every spin along the qubit x direction. So that's why we call it the transverse field. Okay. And this whole model has a global Z2 symmetry generated by this flip operator, and the flip operator is simply the product of all the x operators at every qubit. Okay, so this is the model. So what I want to delve into now is some mathematical structure of the operators that are present in the transverse field Ising model. So what structure do they have? So let's go back to a single qubit, and we'll realize that there are these 4 operators which can be linearly combined by real coefficients to generate any Hermitian operator on that qubit. Now, first and foremost, you have to observe that these objects, namely X, the Pauli matrices here, they will square to identity. Okay. They also have a local commutation relation, which is the same. If you have studied spin half, you will see that these are very much related to the spin half commutation relations of the angular momentum operators. In this case, they are Pauli matrices, so they will pick up the same kind of commutation relation. But you will see as we work through this that the more important relations are the anti-commutation relations. So most interestingly, in addition to having the well-known commutation relations, these Pauli operators also have these anti-commutation relations. You take any 2 distinct Pauli operators and you anti-commute them. Remember, anti-commutation is multiply one way and add the opposite order of multiplication. Add, not subtract. Subtract would be commutation. So this will add up to 0, which means that they anti-commute. Okay, so this is what happens at a single qubit. What happens if I take operators belonging to different qubits? So now you will see that if these operators belong to different qubits, I and j are different, then they will commute. So in doing so, I must clarify what do I mean by this xi commuting with xj. So when I write xi, this must be now thought of as an operator acting on the full Hilbert space. So when I write xi here, what I mean is I have identity operator from each qubit which is not I. When I reach the qubit I pick the x operator associated with the qubit, and then it's all identity operators of all the other qubits. That's what I mean by this xi operator. So these are truly the operators which act on the full Hilbert space of the system. So they commute if the sites are not the same. So this is the main point. So if you look at this, the set of operators that you can make out of these kind of things, I can multiply operators, get new operators and so on. If you do this, you can generate a lot of operators. But the important thing to note is that all these operators are not important for our discussion, are not useful for our discussions, I must say. So what is the good operator content of the transverse field Ising model? What are the operators that are essential to define the transverse field Ising model? Okay, so this is what we are going to discuss. So if you look at the transverse field Ising model, you will see that the xi operator acts non-trivially on a qubit I. So this xi will act non-trivially only on qubit I. If I act xi, it will not act on j, which is, it will act trivially, meaning it just gives an identity action on the qubit j, where j is not equal to I. Okay, this is the point. And what must be understood is that there are total n distinct operators of this kind. They are linearly independent operators, right? N distinct versions of those. Okay, so we have picked something from each qubit, and that's what the xi's are, what we picked from each qubit. The next set of operators that enter the physics of the transverse field model, Ising model, are link operators. So this is very important to appreciate. In the transverse field Ising model Hamiltonian, the z by itself doesn't enter. It is the product of zi plus 1 and zi. The product of z's on neighboring qubits is what enters this link operator. Now, most interestingly, this operator does not act on a single, this mi does, although it has a label I, it does not act on a single qubit, it acts on two neighboring qubits. So it has a non-trivial action on the tensor product state produced by the qubit Hilbert space at I plus 1 tensored with qubits Hilbert space at I. And there are n such operators. So you see that the model, only these operators, n of the xi's and n of these m's, the link operators, they are the ones which are calling the shots. Note that zi by themselves don't enter the discussion as long as you are working with a model with full Z2 symmetry, because a single Z will not be Z2 symmetric, so you will not allow that in the Hamiltonian, for example. Now, what I would like to point out to you is that the Hamiltonian can be written very nicely as a linear combination of these operators mi and xi. And any physical quantity of interest to you that is symmetric under the flip symmetry, can be obtained from these operators. Okay, so we have defined a new set of operators. Xi were not new, of course, we just took them from each qubit. Mi are these new operators we have defined. So let us see what are the properties of those operators. What is the algebra of those operators? So now I am writing this a little bit more carefully. If I square xi, I will get the identity of the full Hilbert space. Remember, xi now, once I write this many body or many degree of freedom Hamiltonian, xi is now acting on the full Hilbert space. See this comment, read this comment again. Okay. And now you will see very easily that xi and xj commute when I not equal to j. That just very straightforward. Of course, xi commutes with itself, so that is not, one doesn't have to mention that. Okay. The second point is, what is the algebraic structure of these link operators? Now, if you look at the link operators, if I square the link operator, I will still get identity. That's the nice feature of the link operator. The link operator is not a single qubit operator, it's a 2 qubit operator. But if I square it, I will get identity on the full Hilbert space of the transverse field Ising model. And you will see that this mi mj also commute with each other whenever I not equal to j. Now comes the first non-trivial result. What is the relationship between xi and mi? Now, noting that mi is actually product of z operators, you will be able to see that xi will anti-commute with mj if j is I or j is I minus 1. Okay? That is because the link I minus 1 and the link I have a common site, which is the site I, and therefore this xi will anti-commute with those link operators. If j is not I or I minus 1, then it will commute with that operator, xi will commute with mj. So now you can see that what I have here is a set of objects which have certain algebraic properties. There are n objects we call them x. There are n other objects which we call m, both of them square to identity, and they have if you have labeled them in some way, they have a certain anti-commutation relationship when the labels are close by, if you wish, and they commute when they are far away. So this is the operator content of the transverse field Ising model. Now what I am going to do is I am going to ask you to reimagine the transverse field Ising model by turning the tables around a little bit. So imagine now, instead of thinking these operators as if they are operators of the transverse field Ising model, imagine you have some set of 2n abstract object, abstract meaning something general, which satisfy the same commutation relationships, which satisfy these algebraic relationship. Okay. So I am just stating that we are going to start with, instead of starting from the Hilbert space operators, etc., we are going to start with claiming that there is a set of objects which satisfies these algebraic conditions. Okay. I am using the same notation, but the sense in which they are written on this slide is different from the sense in which they are written on the previous slide. Here we did not start with the qubit Hilbert space, rather we said that there are objects that satisfy these conditions, right. So I can give you an example. Suppose I tell you that x square equal to 1. There are many solutions for x. So for example, the number 1 will do the job. But I can also have the matrix 1, 0, 0, minus 1, that will also square to 1. 1 being interpreted suitably as the identity of the 2 by 2 vector space, or that 2-dimensional vector space. So this is pretty much that in that sense. So I am writing these equations inspired by what I saw in the transverse field Ising model Hilbert space, and I am claiming that these objects are some abstract algebraic objects. Now what you do, you want to put some more mathematical structure on this. So imagine that these are 2n linearly independent objects and you make a vector space out of them. So you can say, we can in general do complex numbers, but for us real numbers also just fine. You can make a vector space out of them by combining them with numbers, linearly combining them with numbers. So you can generate a set of operators. Now usually in vector spaces we do not have a notion of multiplication, but because these are operators, we have some notion that you can multiply two operators and get a new operator. So whenever you have a vector space, I am being fairly non-rigorous here, whenever you have a vector space and you are able to multiply vectors and get new vectors out, you would call that algebraic structure an algebra. What am I proposing here? I am saying that let us take 2n objects, I am using the same notation, but you should not think of them as Pauli matrices now. These are some 2m objects which satisfy these relations. The question is, can I find a realization for them? can I find, like I gave you an example of x square equal to 1. I gave you two distinct realization for realizing that, for getting that equation concretely as certain objects that satisfy left hand side and right hand side, left hand side equal to right hand side. Okay. So what we have now is we are going to generate an algebra of the set of all xi's and mi's. So how do you generate algebra? These are called generators, the 2n of them. You multiply them arbitrarily amongst themselves, linearly combine them and keep doing this. So you will generate a whole set of numbers, whole set of vectors in that vector space by multiplying many times over and so on, and you will generate a big thing, and that's called the algebra. Okay, so we have started with this abstract set of objects, we have generated an algebra. Now you see, I'll give you a different interpretation of the Hilbert space of the transverse field Ising model. The Hilbert space of the transverse field Ising model is a representation space of this algebra. That means if I have a set of qubits arranged on a line, I can find operators in that qubit space, which we did in the previous transparency, which realizes the algebraic structure of these relationships concretely using matrices, etc. Okay. So we looked at the algebraic relation satisfied by our polymatrices that generated the operators of our transverse field Ising model. We abstracted them out, and now we are reinterpreting the Hilbert space as a representation space of this algebra. Okay. So this is where we are. So have you seen representations before? And the answer is yes. So for example, in your elementary quantum mechanics course, when you studied angular momentum, you said that the angular momentum operators don't commute with each other and they form this algebra, the angular momentum algebra. And then how did you discover there is spin 0, spin half, spin 1, spin 3 half, etc.? You asked the question, what are the representations of this algebra? And then by a set of calculations, you found that there are distinct representations. There is the angular momentum 0 representation, angular momentum half representation, 1 and so on. So once you get an algebra, you can generate representations. So if you treat this transverse field Ising model as being a realization of such an algebra, you have a legitimate question to ask now. Can you produce a different representation of the same algebra? Okay. And this is what we are going to try to find. Can you find another representation of the same algebra? We would ideally like it to be on a different Hilbert space even. In fact, I should generate another Hilbert space, another set of operators and so on. Okay, if you want to try this, you should pause the video now and try it yourself a little bit and then come back. Okay, so hopefully you made some progress. So I'm going to construct this another representation by explicit construction. Right? I'm going to show you that there is another representation which is different from what I start off with. So first what I do is I construct a dual lattice. So what is this dual lattice? So you see, these blue sides are the sides of my original lattice, and this blue line which is in the background here is the link joining the site I and I plus 1. Let's say this is I and this is I plus 1. What I'm going to do is I'm going to place a site which I'm indicating by a square, which is the site of the dual lattice, right at the center of the link joining I and I plus 1. Okay. So what you will get is, when I do this, I will get two things. I'll get these sites on the dual lattice and I'll get the dual links. So remember, the dual links are now sort of sitting on top of the sides of my original lattice. Sides of the dual lattice are sitting on top of the links of my original lattice, and links of the dual lattice are sitting on top of the sides of my original lattice. And you can see that there will be n such sites, there are n links in the original lattice, so associated with each link there will be a dual site. And what I am going to do, this is just for bookkeeping, I am going to associate this dual lattice site and this my original lattice site. I am going to associate them. So, I am going to say this guy is the partner of this guy. Okay. I have already mentioned this. The dual lattice has n sides and it has also periodic boundary conditions. Now, what I am going to do, at each of the dual lattice site, I am going to place a different qubit. It is not the same qubit as I have here. I have a different qubit here. And I am going to place one such qubit in every dual lattice site. And I am going to construct a Hilbert space which is going to be the tensor product of these dual qubits. Okay, that is what I am going to do. Okay, all right. Now, what do I gain out of this? So, if you look at the dual Hilbert space, namely the qubits, the Hilbert space of the dual qubits, I will see that there are a set of Pauli operators associated with each dual qubit. So, what are they? They are the identity, the x, y, all with tildes now to indicate that they are in the dual world. Now, you can generate whole set of operators out of these things. But again, I am going to collect a special set of operators from these collections. So, what are they? I am going to pick x tilde, I tilde, all the Pauli x operators in the dual qubit at the dual sides, and there are n such operators, and I am going to construct link operators on the dual lattice, and I am going to do that slightly cleverly so that things will become useful for me. Usually I define the link between I and I plus 1. Here I am going to do the link between I tilde and I tilde minus 1. So, I am sort of picking the link left. In my original lattice, I was picking the link to the right of a site. So, these xi operators are associated with the dual site, and this m tilde I are associated with the dual link, and they satisfy this condition. They are related to the Pauli z operator at this site and this site via this relationship. Okay, what do I gain out of this? So, now if you take these set of objects which are acting on a different Hilbert space, a different set of operators, they will satisfy exactly the same conditions as what I had in my original transverse field Ising model. Okay. So, you see, you can just check for yourself that x tilde square will become I tilde is identity in the dual space and so on. So, what have I done for you? I have generated for you a different representation of the same algebra that was represented on my transverse field Ising model. So, this abstract set of relationships that we wrote down that are realized by qubits on my original lattice as well as by the qubits on my dual lattice. Okay, so we have got a different representation of the algebra that was the algebraic content of the transverse field Ising model. Now, the representation space is the dual Hilbert space, the tensor product of all the dual qubit Hilbert spaces. Okay, what am I going to do next? What I am going to do is I am going to construct a map going from operators in my original transverse field Ising model and operators in this dual representation. I am going to construct a map. So, watch this. So, transverse field Ising model algebra represented on V and the dual is represented on V tilde, and the map is like this. I say that the operator xi maps to m tilde I tilde. So let's understand what we are doing here. The site operator in my original model is mapped to the corresponding link operator in the dual model. It's a map, operator map. Okay. The inverse map would be, if you will say the link operator here is related, going back to that. At least for these operators, this is well defined. Okay. And the link operator in my original model is going to the site operator in the dual model. So I have made this sort of one-to-one correspondence between the generators of one representation of the algebra and the generators of the other representation of the algebra. So it's a correspondence between generators. Okay, so if I do this, I can immediately find what happens to my Hamiltonian. So the Hamiltonian that I had, H, which is equal to the exchange times the link operators minus H times the X operators, now maps by this map J times X tilde I tilde, which is now a transverse field, and H times the dual link. So what is this? We have arrived at an astonishing conclusion, which is that the quantum dual of the transverse field Ising model that we started off with is also a transverse field Ising model defined on the dual lattice, but with the two coupling constants exchanged, so to speak. So the dual will have J as the transverse field and H as the exchange coupling. So the two objects, the two energy scales, they interchange roles. Okay, I hope you find this exciting, because it really is. So what we have done here is we have realized the quantum dual of the transverse field Ising model. So naturally, we have to explore what are the consequences of such a duality. Okay. So the quantum dual or to the transverse field model is also a transverse field Ising model on the dual lattice with coupling constants reversed, in the sense coupling constants are, the roles are reversed. So what happens? So if I look at my original transverse field model in the small h by j limit, that we would think of it as a ferromagnetic regime of the model, will map to the paramagnetic regime of the dual model and vice versa. So all of a sudden you realize why the answers that we found by perturbation theory were simply exchanging J and H. You would get the answers from one side. If you have done the calculation, you will get the answers on the other side by simply exchanging J and H. So you see that shows up because there is a duality in the problem, and the duality maps the transverse field Ising model to the transverse field Ising model on the dual lattice with reversed coupling constants, if you wish. Interchange coupling constants is what I should say. So this offers an explanation of the the puzzles that were thrown up by the perturbative calculations. Now we have more to say. If you now focus at the point in the parameter space where H is equal to J, then you find something absolutely spectacular. You find that the model is self-dual. What does that mean? That means after the duality transformation, I get back the same model. Okay, it's defined on the dual lattice space, but it's the same model. So this is the idea that it is self-dual. Now, because it is self-dual, this suggests that this could be a point of phase transition, because on one side of H by J you expect paramagnet, on the other side you expect ferromagnet and so on, and you see, just like what we did in the classical story, you can imagine that h by j equal to 1 is the special point where some phase transition takes place. Well, but it does not give you at this stage of the discussion any clue as to whether it is going to be first order, whether it is going to be second order, whether continuous, we do not know. But let me give you an argument to show you that it could be continuous. So, you see, you remember that the domain walls, they were able to hop when you introduce the transverse field term, and the transverse field term acted like the kinetic energy of the domain walls. So, what is the dispersion of these domain walls? So, you will see that is 2j minus 2h cos k. So, the lowest energy state here will occur when k is equal to 0. So, the lowest energy will be 2j minus 2h. Now, see what happens when h becomes equal to j. That excitation energy will become 0, which means that we can have a crude argument, but a physically compelling one, which tells us that the excitation spectrum will become gapless when h goes to j. We will later discover that this is actually true, although some of the details like how it goes to 0, etc., will get modified. So, we'll visit this point later. So, while this is a somewhat of a hand wavy argument, at least at this stage it is enough to convince us that there is some kind of a continuous transition possible, and noting the fact that the value of h at which this gap closes in the simple perturbative calculation is equal to the value that is thrown up by duality, we are encouraged to conclude that this is going to be a continuous transition. Okay. All right. So, this must be very exciting for you because you have now seen an example of quantum duality, but I want to draw your attention to a puzzle here. Suppose h is equal to 0 in the transverse field Ising model, and you did not have any symmetry breaking field or whatnot, because you do not have a symmetry breaking field if you hold on to the full symmetry of the problem. Then the ground space of the transverse field Ising model at h equal to 0, remember, was spanned by the up state and the down state. That means that there are two degenerate orthogonal states which are ground state, and any linear combination of them will also be a ground state. So, that is what you would find in our model, in the model that we studied, the transverse field Ising model. But if I look at the problem in the dual language, then the ground state there is the x tilde polarized, x tilde right polarized state, because j and h have exchanged roles in that dual problem, and therefore has a unique ground state. Then what is the meaning of duality? How can you justify the fact that on one side there is a ground space which is two dimensional, whereas on the other side which you are claiming to be completely equivalent has only a non-degenerate unique ground state? So, something is not giving here, right? Something is puzzling. So, to resolve this puzzle, you have to delve a little deeper. So, remember, we defined these link variables, and if you go back to the classical discussion of the Ising model, we notice that the link variables are not all independent. There is a constraint on the link variables. Exactly that constraint will show up here when we put periodic boundary conditions. So, you will find that the product of the link operators has to be identity. So, if I look at this expression in the dual language, each mi will become x tilde I, and when I product them, I will be producting over the sides of the dual lattice, and I will get the identity of the dual vector space. Remember, if it is a mapping, identity has to get mapped to identity, otherwise you do not have a good map. Okay, so this is the story. But what does that mean? That means this is the flip operator in the dual space. So you are saying that the flip operator is identity. What does that mean? That means that you have to construct a subspace of the dual space in which the flip operation acts as identity. So this is called as the identity representation of the flip symmetry. I can show you this exactly what happens if you argue the other way around. So you see, if you look at the constraint imposed on the link variables in the dual lattice, you will see that the product of m tilde I tilde is also I tilde, which now by duality transformation will force that product over xi is identity. Product over xi as an operator is not identity. The statement is that we have to look at the subspace of my full Hilbert space where it acts as identity. So what we are asking is, we want to work in the subspace of the full Hilbert space which carries the identity representation of Z2. And in fact, what this is showing is that the duality is an exact sort of mapping only in the subspaces corresponding to identity representations, both in my space as well as in the dual space. So in particular, if you look for states that satisfy this condition that the flip operator acts like an identity on them, you will find that the ground state at h is equal to 0 is unique and is in fact exactly this. You can of course multiply it by any phase, but that's not of much interest. But it is this, the phases between these two states have to be exactly +1. That's the main story. That is what will make it an identity representation. So we now understand there is duality, but the duality is operative only in some subspaces of the full Hilbert space. Okay. So since many of you will be interested in open problems in physics and to think about exciting new topics, this is a good point for me to show you how study of such a simple model actually gave deep conceptual advances in the field. So I have to point out that recently these problems have been studied and people ask the following question. At the h is equal to j point, the transverse field Ising model is self-dual. So the question that was asked is, can we make this self-duality into a symmetry? That means, can I find operators which transform, m to x and x to m, right? So this question was asked and the answer was found to be yes, but those transformations were non-invertible. So this gives rise to a very interesting research topic called non-invertible symmetries. And in many ways, this could have been anticipated that it would be non-invertible by simply making this observation that the duality operates only in the singlet sector, singlet meaning the sector in which the flip operator acts like identity. So if you are interested, you should check out this paper by Shao. It's a very, very interesting and very nicely written paper. Okay, so I would like to conclude the lecture now. So the main points we saw in this lecture was we gave an algebraic perspective to the transverse field Ising model. We looked at the operator content of the transverse field Ising model and we abstracted out an algebra, and then we treated the transverse field Ising model Hilbert space as a vector space on which this algebra can be represented. We then found another representation of the same algebra, and then from that representation we were able to infer a dual to the transverse field Ising model, and the dual to the transverse field Ising model turned out to be a transverse field Ising model but with coupling constants exchanged. That is, coupling constant, the j becomes h becomes j kind of. Okay. And this certainly helped us understand why we got this funny looking results when we did perturbation theory. And I hope that I have convinced you that the possibility of these two of first order and crossover has been set aside, and based on all our calculations, we now believe that there is a continuous transition at a value of hc, that is hc by j is equal to 1. So, the h critical at which this occurs is same as j. So, this on this dimensionless scale, this number should be 1. This is what we believe. Okay, I would like to invite you to try out something. Remember, in the last lecture, we saw that the transverse field Ising model in one dimension, maybe a couple of lectures back, can be mapped to a classical model in 2 dimensions. So, what you can do is you can start with our original transverse field Ising model, map it to a classical problem, go to the dual model, map that to another classical problem, and you can try to show what is the relationship between these 2 classical problems. So, you can use that to derive the duality, the classical duality of the 2D classical Ising model. You can also try something else which will be very instructive. So, we used periodic boundary conditions here. So, instead of using periodic boundary conditions, suppose I used open boundary conditions, what would be the dual to the model? That is also an interesting exercise to work out. Okay, so what's coming up next? So, I am in fact going to show you that this transition is continuous, and I am going to show you an exact solution of the transverse field Ising model in 1 dimension. Exact meaning analytical solution of this problem. So, this is what we will do in the next few lectures, and I look forward to seeing you there.